Now we will have second session on day 2 by Sri Ravikiran Garu. And without late, I request Muddada Venkatesh Garu, Assistant Professor, Mechanical Engineering Department, ITAM College, to give brief introduction about Sri Ravikiran Garu and followed by his session. Thank you. Over to you, Venkatesh sir.
Yes, sir. Good evening, everyone. Myself, Venkatesh, Assistant Professor. It's my great pleasure to welcome you all to this session of our Faculty Development Program. Today, we have the privilege of hosting an esteemed industry leader, Mr. Ravikiran P., a visionary in the field of manufacturing and logistics. Mr. Ravikiran currently serves as the Director of Manufacturing and Logistics at Dassault Systems, where he plays a key role in driving innovation and expanding solutions in India's rapidly evolving manufacturing landscape. His academic journey is equally remarkable. He holds a bachelor degree in naval architecture and marine engineering from Andhra University College of Engineering, where he was the department topper. He further pursued an M.Tech in ocean engineering from IIT Madras, achieving an outstanding 9.4 CGPA and earning the prestigious DAAD scholarship. As a scholar, he went on to complete his MS in Naval Architecture and Ocean Engineering from Technische University Berlin in 2004. Mr. Ravikiran joined Dassault Systems in 2004 and has since held several critical roles in R&D and business development. He later enhanced his business expertise by pursuing an MBA from IIM Bangalore, followed by advanced studies in entrepreneurship and innovation at ESMT Berlin, where he excelled with an A+ grade. As a key industry figure, he has played a pivotal role in Dassault's double-digit growth in India over the past 4 years. He is also an active member of renowned organizations like the Society of Automotive Engineers (SAE) and the Indo-French Chamber of Commerce and Industry (IFCCI). Beyond his corporate success, he is a strong advocate for the future of manufacturing, focusing on virtual twin, artificial intelligence, robotics, and IoT to drive smart and autonomous manufacturing. We are truly honored to have him with us today. His knowledge and experience will offer invaluable insights into the transformative trends shaping the future of manufacturing and logistics in India. With that, I warmly welcome Mr. Ravikiran Garu to deliver his session. Sir, you can start your session, sir.
Thank you. Am I audible?
Yes, sir. Yes, sir. Audible.
Audible. Okay. Very good evening. Actually, Professor Sri Hari called me and asked me to do this session. But coincidentally, I'm traveling. I'm still in Europe, but I could not say no to Sri Hari because we studied together. We are classmates. We are good friends. There is no way I could say no to what Sri Hari asks for, regardless of which part of the globe I am traveling. So thank you very much for giving me this opportunity. I remember doing such a session in 2020 during the COVID period, I guess, to
Yes, sir.
a similar session, and but it is on a different topic called advanced techniques and in manufacturing and what's happening. How advanced manufacturing techniques will help an enterprise in becoming relevant in today's market. Okay, so thank you very much. I think it's probably, what time is it? 7:30 in India. I guess it's late. I don't know how Shri has created this program at such a late evening. If it is for me to accommodate me, my sincere apologies for keeping you so late in the evening. But I'll assure you that in the next 1 hour of the time I spend, I'll give you a quick insights of how digital manufacturing, that's a topic he has given me, how digital manufacturing is revolutionizing in aerospace and shipbuilding industries. Okay. Thanks a lot for such a nice introduction. It is a very humbling experience for me to listen through my life's journey in my academia and professional career. Thanks a lot. Let's dive into what is digital manufacturing. Okay. Um, Although the topic given to me is digital manufacturing, I want to tell you that digital manufacturing is past. Okay. You might be wondering that here is a person who is asked to talk about digital manufacturing and he's talking about that this is no more current or future, it is past. I say it for a reason. Digital manufacturing is still there, but digital manufacturing is now called virtual twins, and there is an evolution of this topic. It is not an old wine in a new bottle. It is completely different, and it brings in a new perspective at the way we look at digital manufacturing and what it does. Uh, some people call it digital twins. We call it as virtual twins. There is a subtle difference between what is digital twin and virtual twin. Probably today is not the time I'll spend, more about giving you the difference between what is a digital twin and what is a virtual twin. But the point I'm trying to make here is digital manufacturing is nothing but a technique where you manufacture before you take any product to the shop floor. You manufacture, carry out various manufacturing what if scenarios in the virtual world using computer softwares and technologies and all of that. That is what is we all know as digital manufacturing. So you might be wondering what is virtual twins and how these two are different. Is virtual twin a new nomenclature for digital manufacturing, or is there more to it? Okay, so I'll set that context and then we will deep dive into how this is going to um, affect or help these two industries, aerospace and shipbuilding industries. Okay. In today's world, we are grappling with two worlds. The world where we model, design, simulate, which is what is virtual world. This is where we have a bit of a, how do I say it? You can experiment it, and it is okay to fail. It is okay to get wrong. But there is another world called real world. The real world is very, uh, very cruel, if I may have to say it that way. And there is no undo in the real world, right? Unlike the virtual world where you can click a Control Z and undo whatever you have done, you can undo your simulation, you can undo your model, you can undo everything. And in ChatGPT world, you can create new things. But in the real world, yeah. Sorry, is that a question?
No, Ravi, go ahead, please.
In the real world, there is no undo. So how companies, be it aerospace or shipbuilding or any other automotive, any other company, they start creating the assets in the virtual world, but they start realizing that in the real world. And these two worlds have to operate in sync so that they can get best markets, time to markets, okay, more qualitative products, more end user experiences. And this is what the consumers are looking for. And how do we achieve it? What happens from virtual twin to real world is this is where you create virtual twins. That is a journey from V to R. In the V world, you innovate. This is where you experiment. You create various kinds of models. But the models could be, if you take aerospace, the L by D ratios of the wings, the aerodynamics of the aircraft. And there are so many things. Today we are talking about solar planes. How do you put this energy consumption or energy, how do you absorb the solar energy to propel the aircraft? So there are so many concepts that are coming up. So you can model all of these things in the virtual world, and that is where you can innovate. That is what we call it as design and engineering aspect. And what do you do in this virtual world? You create product twins, plant twins, and process twins. What is product twin? Nothing but creating a 3D model of a aircraft or a ship or a car or anything. What is plant twin? Why are we saying plant twin? Just like the way you can model your cars and ships and aeroplanes, you can also model your factories. It is very important to model your factories because there are so many what if scenarios that you can validate. So plant or factory twins is also important. Okay, that's also part of digital manufacturing or a virtual twin. And the third aspect is process twins. What is process? Process is nothing but a sequence of steps that you carry out to start from a raw material to an end goods, end product. So you carry out so many operations. It could be forming, casting, machining, assembling. So there are so many operations that you carry out from a raw material. Raw material could be a simple steel plate or a sheet metal in aerospace. Okay, you start with these, and you eventually, after carrying out so many operations, it becomes a car or an aeroplane or a ship. So this process, the sequence of operations that take the product from a raw material to the end product is what is process. It is important to also to model these processes so that you can tweak. What if I do this first? What if I do the operation 1 first and 2 later, or 2 first and 1 later? So you can do the sequencing, parallelizing operations. You can bring in so many efficiencies also, not just about innovating, but also efficiencies into your process. So in the virtual world, you model your product twins, plant twins, and process twins. And then once you have done all of that, you throw it over to the real world, that is to the shop floor, and tell the people that, okay, I have a model, I have drawings, I have the shop floor, which is, the layout is fantastic. There is an absolute, almost 90% of overall equipment effectiveness and productivity. So let's go. And then comes the real world. And the real world, as I said, is very cruel. And it always throws surprises and shocks. It never behaves the way you planned. And the real world is where you start observing what can go wrong. No matter how well you plan, things go wrong, because that is the dynamics, that is the volatility of the real world. You are expecting a material to come, and that material didn't arrive for a reason, that the truck got broken down, the particular part is got stuck in customs. There are so many reasons why things can go wrong. And you are waiting for a big component which is part of your assembly operation that day, and it did not arrive. The shop floor is waiting for it, and shop floor is not doing anything. That means you have lost 1 day. So the real world, regardless of how well you plan, will continue to throw surprises. From those surprises, we learn. And that's the journey from R to V. The real life insights that will help you to learn, and that learning is put into your virtual twin models. And here is where I pause and probably cannot ask you, because it's not a face-to-face. What happens when you create a model and teach that model? What is happening? What is that called? Everyone knows it. You create a model, and that model starts learning from what's happening in the real world. That's artificial intelligence, right? You have a model, and that model is understanding from the real life insights, and it is becoming better and better. So this is the manufacturing world, and this closed looping is what we call it as the power of virtual twins enabled artificially intelligent engineering operations or industrial operations. So in summary, the digital manufacturing has evolved to become artificially intelligent. And how did it become artificial intelligent? For anything to become artificial intelligent or AI ready, you should have a model first. You should have data first. Model is coming from virtual twins. Data is coming from real world operations. That data is plugged into virtual twin, and the virtual twin starts learning from it and starts becoming artificial intelligent. And thereby, what you're doing, you are creating new products, new plants, new processes that are much better than your earlier versions. This is the evolution of digital manufacturing. And this is the future of digital manufacturing. And AI is not just limited to the software engineers and IT geeks. AI, please be ready. AI is knocking your doors, guys. Is knocking the doors of plants, shop floors, design houses, and all of that. And there is a lot more that I'm sure you're doing a lot of Googling. You'll figure out how AI is. You can now click off a button or giving a prompt, you can design a car. You don't have to do all these flashy, you may wonder that it might be discouraging for a mechanical engineering graduate who is spending 4 years to design an IC engine. And here somebody is telling me that you just have to put a prompt with some text and some questions, and suddenly it creates a IC engine. Yes, that's going to be reality. And the reality is propelled by virtual twins. Okay. Now, having said that, having given you a sneak peek into future, this is not current. It is still work in progress. While we have seen generative AI from ChatGPT, ChatGPT creates documents, create PPTs, create mails, and create so many things. But there is one problem with that. None of those things are engineering compliant. They don't honor physics. They don't honor any principles of physics. It's easy to create a document because if the document is wrong, nothing is going to happen. But it is very important that you create a car right, because if you don't create a car right, it can lead to accidents. So is aeroplanes, so is ships. So creating a simple dummy document using ChatGPT is a very easy task, but creating an engineering, physics adhering, safe, secure industrial product is a different ball game. And that's why I'm saying it's still future, but there is a lot of research that we are doing at Dassault Systems, and there are so many other companies that are investing a lot of money into their research and development to bring out this generative experiences or generative product design and product manufacturing capabilities into the technology. Okay. With that context, I'll having set the context about digital manufacturing and how digital manufacturing is evolving into virtual twins and how virtual twins are becoming the foundation of this AI of industrial operations, right? I just pause here so that you internalize this message that how digital manufacturing is evolving into an AI-driven industrial operations. Now that I have set that context, now I'll give you some examples of both aerospace and shipbuilding industries, because is what Shri has requested me. But here is where we may look at some of the traditional things. Obviously, the future is still getting ready, and I'm not entitled to share that yet. It is still confidential IP. I wish I could share that probably next year when we do the session. I'll share some more about the generative AI-driven design and AI-driven manufacturing capabilities. Now, coming back to how digital manufacturing is critical, how and why digital manufacturing is enabling these industries, especially the players in these industries, is what we will look at now. Okay, I'll take a quick 1 second pause for you to internalize that message, and also a sip of coffee for me. Okay, now let's come to aerospace industry. Aerospace industry, if you have seen, I think today, 10 years ago, people would have known that there is an aircraft and I fly. Nobody had interest in aircrafts as much, barring the aerospace engineers. But today, everybody's interested for good and bad reasons. The good reasons is that flying is always, and when I flew, my first journey, I still remember I was 20 years old, and when I took my first aircraft, it was an exhilarating experience to be on the clouds and to experience the journey, right? It was good. But in the last 10 years, there were so many aircraft accidents, okay, especially Boeing 737 MAX. And that has garnered the interest of even common people. What used to be interest of high-tech aerospace engineers has become a matter of interest even for commoners because of seeing these so many accidents. So what is going wrong? Why are these aircrafts that is considered to be the safe mode of transportation is now getting into so many issues? As recently as a month ago, we have seen an accident in South Korea, one of the airport where the aircraft landed and the landing gear did not open, and then it went into crashing to the boundary wall and losing almost all the lives on the aircraft. So the aerospace industry, the paramount aspect is safety, okay? Because when you're flying in the air at 30,000 feet level, there are no chances, or in fact, it cannot afford, not even crash, it cannot afford any small turbulence also, right? That's the endeavor of these companies. But what's happening, why are we getting into this mode is because the aviation sector has exploded in the last 2 decades across the globe, especially Asia. 20 years ago, I think very few people were traveling in aircrafts. Today, if you see, airports have become bus stations almost. Airports are busier than bus stations today. That's a good sign in India. It's good that people are having more purchase parity. We are growing as an economy. It's a good side. But with this demand for newer and newer aircrafts and more aircrafts, most of the aerospace companies are falling behind the schedule. Just to give you an example here, there are almost 5,900 aircrafts in backlog in 2017, by the way. This is a bit little older. Today, the recent information that I have, the COVID has partially helped because there were lesser aircraft orders. But even after COVID, again, the aviation has picked up. Today. Almost there are 10,000 orders in backlog. Boeing, Airbus, Embraer, all these companies are now huffing and puffing to meet this demand. So, which is a very interesting thing. There is more demand, but they don't have enough capacity, enough capabilities to deliver the demand. And this is where digital manufacturing comes handy. First thing, how can I produce more with what I have? That means I have only few plants. Can I produce more and more? If I'm producing 10 aircrafts, can I make it 20 aircrafts a year from that particular line? So to do that, what do I do? Okay. And how do I modernize my existing facilities, which is very important because the newer equipment brings you better efficiencies. Then the second part, as I said earlier, because of this rush deliveries, there were some quality issues which we have seen with Boeing 737 MAX. So it is becoming even more paramount. The regulations or the regulatory demands have increased on aeroplane companies. So it is important that the non-conformances are reduced. The first time right is being looked at very keenly. That means the shop floors and the factories have to become more and more quality compliant. And production profitability and competitiveness. Once again, there are so many players that are coming into space, and there is a lot of competition amongst players. So when there is competition, the profitability reduces. When the profitability reduces, people tend to take shortcuts. Now, how you can maintain your profitability while being competitive? That means you have to adopt new methods, new materials. If I use a composite instead of as a regular sheet metal, my fuel efficiency will increase. With maybe 1 gallon of fuel, today I'm flying 1,000 kilometers or 10,000 kilometers, sorry. You may fly even more, right? So how do you bring new materials and new methods of manufacturing so that your operational costs are reduced? This is where profitability comes into picture. It's not just about how much, what is the cost of making it. It is also important what is the cost of operation. A lot of people tend to ignore that, right? That is where the competitiveness by introducing new systems, new materials becomes very important, and new methods of manufacturing from the shop floor context. And then the supply chain dependency. Today, even in India, we have so many Tata Advanced Systems, Tata Aerospace and Defense, Mahindra Aerospace, Godrej. All these companies are making components of global aircraft companies. For example, Boeing 737, I think empennage is made out of Hyderabad. And similarly, the helicopters, Sikorsky helicopters are made out of Hyderabad. The cabin, Sikorsky helicopter cabin. So what do I mean by this? Although the assembly units are in US and in Europe, these components are distributed across the globe. Some are getting manufactured in India, some are getting manufactured in Vietnam and Taiwan and all these places, and China probably, and they all have to be shipped and assembled in US. That means what? The company has to ensure the quality standards across all these entities, and they have to ensure right assembling techniques so that there isn't any material wastage or time wastage when they bring all these pieces together. So the supply chain dependency becomes more and more critical. So because of these, business, I have given you a business outlook because it's very important. I know most of you are engineering graduates and you think technically, but it is very important as to why there is a need of certain technology. Every technology is nothing but an application of science, and it exists to address a certain business problem, right? So the business context is always important. I just have spent some time to give you the business context. So how can, as I said, they have to produce more and more with the same capacity. That means they have to produce more per hour. And how can they do it? Can we have a flexible production system? Flexible production system is a production system which can be tweaked based on the demands and the product variants and configurations. Production quality, as I said, ensuring production quality is paramount in aerospace engineering. There are so many ways and means to track the quality during production, during assembly. Today, there are so many devices that have come on the shop floor which can monitor what is the torque I have applied while screwing a bolt or a nut. Okay, even those parameters can be captured automatically. Not even, there is a auto torque which screws it, and then you get the parameter whether it's within the range or not. So there are so many ways and means of carrying out these assembly, riveting, bolting, and welding activities, and this is automatically captured by these IoT systems and tell you whether they are within the range or not. That means the quality is not gone are the days where quality is inspected. Okay, quality is built in. That's how the manufacturing is evolving. Now people are not waiting for quality conformance. They're waiting for quality assurance. What is assurance and conformance? If you check for the quality after the job is done, it is quality conformance. If you ensure that the quality is built in, it is quality assurance. So that's what is happening. More and more quality assured products are becoming, and there are so many new methods and ways and industrial equipment that have come handy to enable these aspects. Profitability and competitiveness. I mentioned this. This is where we are talking about new materials. Can I use carbon composites? Can I use glass and fiber composites? So there are so many ways and means of introducing new materials that can reduce the overall weight of the aircraft, thereby improving the operational efficiency, fuel efficiency. And improving fuel efficiency is not just for profitability, but it's also sustainability, because the reduction in the carbon footprint. Similarly, in the factories, not just the aircrafts, even factories are a big carbon footprint creating entities. Okay, today there is a lot of emphasis by the enterprises in ensuring that their factories are sustainability regulatory compliant. That means the energy consumption has to be optimized. What kind of energy sources they're using? Is it a renewable energy or a thermal non-renewable energy sources? What kind of water resources they're using? Any other natural resources they're using. Raw materials like metals that they are consuming. So there is a lot of focus on how less can we use to build the same product, how optimally can we deliver the same product by minimizing the wastage. So that's also adding to the profitability and the sustainability dimension. And supply chain dependency, how to transform supply chain. There are so many disruptions, as I said. COVID pandemic was a disruption. The entire supply chains got halted. We could not have done much about it. But even in the case of these pandemics and then or any geopolitical tensions, how do you still continue to operate your supply chain so that you are not missing out on your deliveries? These are the industry's needs. And to meet these needs, as part of our manufacturing, what you see here in the slide is, on the left, what you see as winning concept, program excellence. These are all, you can read that, these are all the various activities of aircraft manufacturing. Okay, system requirements, manufacturing requirements, structure creation, lofting, concept bomb, product evolution, scheduling, change management, manufacturing bill of material, assembly instructions. So what are all various steps or various phase gates of aircraft manufacturing? In today's context, because we are focusing on digital manufacturing, what I'm going to emphasize on how you are going to address these four components: the production rates, the profitability, the supply chain network, orchestration, and then the final one is the entire scheduling and activities, right? So you see here, let me put a cursor if I can bring a, yeah. So this is where you get your demand. This is entire your S&OP planning or the supply chain planning. Okay, you have a demand, and to meet the demand, you have certain capacity. How do you balance your demand and supply? Okay, that means you have to outsource a lot of activities. It's more of a business, kind of an industrial engineering and industrial management topic, maybe not for the core engineering folks. But here is where we see the engineering core engineering topics. Plant and production line layout pre-study. Okay, how do I reconfigure my lines so that my lines can be more productive and there is a better overall equipment effectiveness within my plant? And when you're doing assembly process and virtual build, how can I minimize my the clashes? And how do I, sometimes you leave a lot of material for tolerances and you end up seeing a lot of gap. So how do you maintain this GDT, the dimensioning and tolerancing, and ensure that there are lesser and lesser clashes as you bring so many components together? And you can achieve this only by doing a virtual build of the aircraft. So this virtual build will facilitate you to bringing these components together, ensuring that the models are rightly designed, and then only you share these drawings and models to your supplier organization so that they can go into manufacturing, right? How do you validate that? And when it comes to part fabrication, aircraft industry can be broken down into two things, two key manufacturing aspects. One is fabrication and one is assembly. In fabrication is where you take a sheet metal and make it a wing or make it a fuselage, right? There are so many shapes that you get into. So that is all fabrication activities, and this is where you use machining, you use riveting, drilling, and you use a bit of a robotic activities as well in terms of bringing these two pieces together. The second big activity is assembly. Assembly is where you bring 2-3 components together and rivet them. Riveting is nothing but an activity, unlike shipbuilding, which is welding. In aircraft industry, you do the riveting. So rivet them so that these both parts are brought together in a better fidelity and integrity. Okay? That is the second step, the assembly process and part fabrication process. And then scheduling, how you leverage your existing shop floor and ensure that if you're having 3 shifts, each shift of 8 hours, how you ensure that you are sweating the assets. The organization can only make profits and deliver the rates only if they sweat every asset for its full time. That's when you can improve your overall equipment effectiveness as well. So these are the key aspects that are part of, we call this as ready for rate. What do we mean by that? By putting these technological components, by carrying out these studies before you take the aircraft for manufacturing in the virtual world, you can improve your delivery rates. That means you are ready for the production rates that the organization is expecting. And by doing this, these are the benefits, deliver rates. I'll not get into this. These are more of business outcome statements. But what I'll do is, these are the 4 key aspects, right? Deliver on rate, optimize your part fabrication, increase competitiveness, and lean supply chain. And each of them have some detailed techniques. I don't know how long are these videos, but what happens in part fabrication process engineering, right? I'll play this video. Let me know if you can hear the audio.
Visualization and documentation of fabrication.
Can you hear the audio?
Yes, sir.
Okay.
Strategies for elementary parts. By leveraging the 3D Experience platform and connecting the dots between engineering and manufacturing, users can define 3D model-based manufacturing BOMs and manufacturing routings with full accountability in a unified user experience. The seamless collaboration between disciplines in the platform ensures that all design and fabrication requirements are considered and met. Validate the fabrication processes for existing and new parts, leveraging their full 3D definition to secure first-time quality and desired rate. Visualize, trace, and consume all engineering and manufacturing requirements in an immersive 3D environment to make sure nothing is forgotten. Leverage the 3D Experience twin of shop floor assets and tools to build clear and concise 3D manufacturing work instructions for operators. This allows a product program to utilize 3D work instructions to shorten the learning curve for new workers.
Yeah. So I think it's more or less self-explanatory, so I'll not spend much time on it. So what it is showing is when you're carrying out a part fabrication activity, how you can ensure from your knowledge that you're building over a period of time, how you can leverage that knowledge readily for creating a new part. And while doing so, how you can transfer the part fabrication work instructions to your shop floor so that they can follow those instructions and ensure the right activities are carried out with right tolerances, right? That is part fabrication. This is one of the steps of aircraft part fabrication standpoint. Now we will look at assembly, process engineering, and virtual build. I did mention earlier that assembly, when you do the virtual build, it is virtual build because you're not building it in the physical space. By doing the virtual build, you are saving a lot of money. And how do you do that? Because there is a lesser wastage. You're not taking it into production unless otherwise you validate the virtual build. This is what we call it as digital mockup, which you're very well aware. It's also called as virtual build. How this can be carried out and what are the benefits of it is what you will get to know from this video. Sorry.
Assembly process engineering and virtual build focuses on manufacturing engineering for assembly procedures. By leveraging the 3D experience and by connecting the dots between engineering and manufacturing, users can define 3D model-based manufacturing BOMs and manufacturing routings in configuration with full accountability. The seamless collaboration between disciplines in the platform enables agile change propagation between design and manufacturing with full traceability. The 3D Experience platform navigates through the links between engineering and manufacturing data, allowing users to efficiently build lean working sessions with only the necessary data. Accelerate the introduction of new product lines and variants by leveraging workload balancing capabilities built into the 3D-based process planning applications. Use the 3D process plans to simulate and virtually validate innovative assembly procedures, ensuring first-time quality for existing and new products. Seamlessly generate 3D manufacturing work instructions for the assembly processes and keep them up to date with respect to incoming engineering changes and updates. Publish the 3D work instructions for web view, visualizing them as any shop floor operator would, and ensure they will shorten the learning curve for assembly workers handling complex aerospace products.
Okay, so here I would add on top of this context. We call this as a PPR context. What is PPR context? Product Process Resource. This is a very interesting topic. Any manufacturer is in the business of building a product, and to build a product or to produce a product, he will follow a process. And obviously, to execute that process, he would need certain resources. That resources could be human resources or machines or robots or whatever it is. So how you can bring these three pieces together? Okay, product, process, and context and resources. Contextualizing all these three elements. Sometimes, what do I mean by this? Sometimes the virtual build of the product is okay. You may see a fantastic, it's good. But only if you bring the resource, the robotic arm may not be able to reach that particular area. So when you're just assembling the virtual build or doing a digital mockup, components are coming together easily. But when I bring the context of resource, which is a robo or a human who has to put a hand and weld or rivet, he doesn't have access. So what happened? What looked to be a right assembly has suddenly become not so right assembly because it is not giving access to the robotic arm or a human arm. So that's why it's important that you carry out the virtual build or digital mockup by putting product, which is your end goal, process, which is your operation sequence, and resources, which are used to carry out and execute this particular activity. All these three have to come together, and that is when you are carrying out a real virtual build. And that's what is captured in this video. Okay, and by doing this, by carrying out these activities in the virtual world, I strongly urge, I don't know, Dr. Srihari, whether you agree with me. The importance of knowing technology is how it is affecting, what are the outcomes it is delivering. It is not just technology for the sake of technology. So I'm bringing these topics of what is it you achieve. You achieve gain in efficiency because you are able to plan it better. You are improving your production rates. You are reducing your, errors. When you reduce your errors, you're reducing your rework. When you're reducing your rework, you're reducing your scrap, because rework means there is a scrap. You're reducing your scrap. When you're reducing your scrap, trust me, you are becoming sustainable, because whatever material that you're using to build is nothing but a metal that is, mined from the earth. So by not doing a rework, by not doing a scrap out, you are only saving the natural resources. And when I say natural resources, not just energy and water, it is also the metals that we are mining from the earth. Right. So these are all the benefits that you get out of these technologies. I'll not get into what are the benefits that some other customers have gotten from this. Then we'll get into the optimization platform. So it is more about the current thing. What you have seen is part fabrication and assembly process engineering. Then we go a little granular. In part fabrication, you do NC programming, you do NC simulation, the tool path validation simulation. Similarly, robotic programming, when you're using a robot for assembling two pieces together, even before the real shop floor robo operates, you want to ensure that the robo is having the right programming with the right degrees of freedom and all the movements, so that it is putting the parts together in a right fashion. So there are technologies that enable you to carry out in the virtual world, and that's what we'll see now. First, we'll begin with NC programming and simulation.
Programming and simulation focuses on the definition of all required NC manufacturing programs with integrated simulation capabilities and best-in-class toolpaths. By leveraging the 3D Experience platform and connecting the dots between engineering and manufacturing, users can ensure future production rates and quality through simulation and optimization with a 3D Experience twin of their production systems to decrease material usage and changeover times. Program and machine context for increased quality and reuse company-wide cutting tool catalogs to avoid data duplication and to decrease costs. Use a unified collaborative platform to program the whole set of NC machines present in the shop floor for lathe, milling, and wire EDM, and leverage built-in simulation capabilities to identify potential costly manufacturing issues. Validate programs and export ready-to-use machine code in standard formats to support machine execution on the shop floor.
Yeah, I think this video is very highly self-explanatory. So you are doing the NC programming, any machining activity, you have a tool bit and you have to define its program. You want to simulate its path first before you execute this in the real time. So this NC programming and simulation capabilities will offer you to do this in the virtual world before you deploy it in the real world. So what you can do is you can take this program and feed it into your CNC machine. And those machines, there are so many machines coming from Fanucs and Kukas and the Siemens. There are so many machine equipment vendors. They take this program directly, and that the machining tool paths automatically adhere to the program that you have already validated. Okay. Similarly, it is a similar logic extension to robotic programming. I'll just also play this video.
Robot programming and simulation focuses on the creation, simulation, programming, and validation of 3D robotic cell layouts, devices, and work cells for diverse aerospace robotic applications. By leveraging the 3D Experience platform containing thousands of robot models from multiple manufacturers, you can design the most efficient complex production system. Use the 3D Experience twin of your manufacturing facilities to virtually optimize robotic processes and greatly increase production rates. Detect any potential manufacturing issues by virtually validating tools and processes to save production costs and increase overall quality. Simulate the behavior of complex, automated production lines with multiple robots to increase and optimize resource utilization throughout offline programming. Choose the best trade-off for your manufacturing studies. Intuitively program diverse robots by easily creating and managing ready-to-download robot vendor-specific programs. Accelerate the creation of the 3D Experience twin for factory of the future or existing facilities using a point cloud solution and the resource catalogs available in the platform. By leveraging the 3D Experience platform, users can seamlessly collaborate engineering changes into the programming processes for quick updates.
Perfect. Okay, and again, we will not obviously go through all these videos. Will be short of time. I have a hard stop at 8:40. Shri, this is still 9 p.m. Is it this particular Dr. Shri?
Yes, Ravi. Yeah, it's 8:20 here.
The time is still 9 p.m. Right? We have time till 9 p.m. Is
Yeah,
that
till 9 p.m. Yes, yes.
okay? Okay. I'll try my best to be here till 9 p.m. I have a hard stop as I told you, but I'll see what best I can do. Okay. Similarly, we have the robotics is used for various activities. It could be painting, it could be riveting, it could be for assembly activity. So I'll not repeat this particular video because it will have a similar activity. But this is an interesting aspect. Aerospace industry is slowly but certainly recognizing the additive manufacturing. Okay, and additive manufacturing is known to all of you, also called as 3D printing, instead of the traditional subtractive manufacturing. What it does is, while the certification and the regulatory agencies are not certifying these parts for key components or the load-bearing components, but at least in the internal components, they are approving the usage of additive manufacturing components. So how, while machining and various other activities are removal of material, right? That's what you do. Typical manufacturing is about take a stock and you remove, you modify the shape of it and all of that. That's how we do it. Additive manufacturing is about creating, putting the layers of materials and creating, like printing it from scratch. While doing so, you add in the way you hold the part. You can create the part in a vertical fashion, horizontal fashion, the angle in which, the orientation in which you keep it, and then the deposition of material will create certain brittleness, certain defects into the part. So this additive manufacturing tool, what we have, tells you what is the best way of creating or a deposition of material, and what is the best orientation of the part, so that your the defects into the part are minimized or reduced. In fact, you can also simulate that and see, once you do this, there are two simulations. One, how do you what is the best orientation and what is the best way to deposit the metal or material. Second thing is, once you complete it, what kind of stresses that got built into this because of the layered deposition approach. So both of these can be validated using this particular tool.
Manufacturing focuses on leveraging the digital thread provided by the 3D Experience platform to author and optimize additive manufacturing processes, ensuring first-time quality. This 3D Experience environment connects design, manufacturing, and simulation to prepare design parts for 3D printing by automatically generating optimal supports, machine-specific scan paths, and produces ready-to-use outputs. Accelerate the adoption of new technologies with shorter lead times, reduced material costs, and a maximized return on investment. Use the virtual twin experience of actual shop floor equipment to accelerate process planning of additive manufactured parts that are produced with different technologies, such as powder bed or material deposition. It can also be used to efficiently generate programs in native format using machine-specific parameters. Thanks to a seamless integration between manufacturing and multi-physics simulations, part distortions can be predicted, as well as residual stresses and as-built material behavior defined by simulating the virtual print process. Easily export validated programs to the
So these are all the granular activities. So we spoke about part fabrication and assembly. Within the part fabrication, you can use NC machining, you can use additive manufacturing, and within the assembly, you can use robotic assembly, and then there are robotic offline programming, simulation, and carrying out actual assembly activities. Right. This is what we have covered as part of the two levers. And what it helps, probably I'll share the slide deck with your team so that you can spend some time on it as part of your study. Once we have done this, is so far what we have looked at is how I can validate my process. whether it is fabrication process or assembly process. You're only validating it, you're only making it perfect in the virtual world. But then there is another thing which I said is planned. How do you ensure that whatever plant you have, factory you have, it has the best and optimal layout in terms of material flow, in terms of information flow as well? And then what kind of scheduling, because there is always the material flow. One machine operates and then it throws that particular equipment part to another machine. So there should not be any waiting period. There should not be a case of where material is waiting for the machine or machine is waiting for the material, right? So this can be achieved with the right scheduling. And there is another interesting thing that is coming up is there are so many new factories coming up in India, not just for aerospace, but it is renewable energies. There are so many plants that are coming up for battery manufacturing in India. Reliance is investing heavily, Adani is investing heavily, and so is solar, wind. So with so many manufacturing plants, there are line builders who set up these plants with the right equipment. And when they set up this equipment, there is something called virtual commissioning. That means you don't have to commission it and then find out the problems in the plant or line. You can commission it virtually. That means you can create a virtual factory. Commission, when I say commission, you can literally start the activities in the virtual world. There is something called a behavioral simulation that is built into it. It behaves exactly like the way the machine should behave in the virtual world. The output, input, logic, signals, and all of that are given. And you see whether the machine is behaving like that or not. If the behavior is a little bit here and there, you have to tweak the behavioral aspects by using model-based systems engineering concepts. And then after doing all these validations, only when you are certain that your line can be commissioned, it has all very good handshake amongst equipment, that's when you go for commissioning. This is what is called as virtual commissioning. This virtual commissioning is finding a lot of fanfare. A lot of companies are adopting it because once you deploy the line, any issue that comes in the line will halt the line. That means losing production time, and losing an hour's production time is losing almost worth millions of dollars for any shop floor or any plant. So virtual commissioning is another important aspect. I'll take you through all these things. This is what about while we have covered the other two pieces about how you prepare your manufacturing process, validate in the virtual world. This particular piece is about how you prepare your plant itself, okay, before you start operating out of it. Okay, so let me play this, which talks about plant layout studies.
Design, simulation, validation, and optimization of factory layouts early in the design process for new industrial assets or to upgrade existing ones. Leverage the 3D experience platform between product design, manufacturing, and industrial engineering to anticipate and resolve any potential production layout issues. Build 3D experience twins for existing or future facilities using your point cloud and an extensive industrial asset resources catalog natively available on the platform to virtually validate designs. Simulate the behavior of the envisioned factory layouts with respect to preliminary manufacturing processes to validate the production line's robustness against multiple what-if scenarios. Through these simulations, identify cost-saving points and reduce unnecessary waste. Thanks to the integrated manufacturing and factory flow simulations, you can estimate cycle times, monitor resource utilization and availability, and identify potential shop floor bottlenecks to secure new product introduction in existing or newly designed production facilities. This will allow users to really use the 3D experience twin to validate and optimize resource positioning and use.
Yeah. This factory flow simulation is based on discrete event simulation technique. Because predominantly most of the activities that happen in the shop floor are discrete events. And how you model these discrete events and carry out this discrete event simulation, which is a very well-known mathematical technique, simulation technique. So using these discrete event simulation concepts, we can carry out a factory flow simulation. How is the flow? Which particular station is bottleneck? How do I solve that bottleneck? If by solving that bottleneck, am I creating another bottleneck in another station? So all of these things can be validated. So before you set up your factory, you take the layout and you build the plant. There is there are a lot of catalogs available with all these standard equipments. Could be conveyors, could be machines, robots. Everything is already available as catalogs in the technology. You can use those catalogs, quickly build your factory in 3D. Then it's not just a dummy 3D model. Then you build the behavior. The behavior is this factory flow. So how your material will flow, model it and simulate it. Then as you simulate it, it'll identify which all stations are your bottlenecks. Then keep solving those bottlenecks. And with so many iterations, you get to a best factory flow and plan factory layout. Only once you have that validated, simulated factory layout and flow, you take that and then start building a new factory. Right? So these are all before you build a new factory. But please do not misunderstand that it is only for new factories. Even in the existing factories, you can reconfigure your lines. I don't know whether you remembered at the beginning, I spoke about flexible production. What is flexible production? Have the same factory, but use it to build different product lines. Today, automotive industry does it. They keep changing variants and they quickly reconfigure the line. They were producing, say, take Tata, they're producing Nexon as a variant. Now they have to produce Curvy. And if they have to phase out Nexon, they may use the same line, reconfigure it a bit and start producing it. So every new car variant doesn't necessarily have to mean that you have to build a new factory. And this factory flow simulation and plant layout technology can be used not just for the new factories, but also to reconfigure your existing factories for new products, new product introduction. Master production scheduling, I'll skip this in the interest of time, but it is nothing but, okay, I'll keep it quick probably. How long is this video? Just 3 minutes. Let me play this. It's an interesting topic. The reason is this is a topic that is an intersection of your engineering topics and your industrial management topic. So it may be of interest to some of your students. So let me play this.
Capabilities of the Delmia or TEMS production station for work orders with details are provided for your review. By hovering, we are presented with additional data for work orders with the ability to add interactive operational information. Expanding the time horizon from weeks to days to shifts will reveal details on the Gantt. The production highlight screens represent production by machine and work order. It shows relationship of the work orders for a particular machine. By splitting the window, you see all the work assigned to a machine with the various links. We also see indicators of the work order scheduled start and end dates shown by the red and green arrows. In addition, the display colors indicate advanced and delayed operations machines. Setup time optimization gives visibility and optimization of setup time.
Yes, you are.
Sir, is the software is made by customized software or it is the commercial software that industries are using?
No, this is industrialized software. Most of our customers are already using it. It is commercially available off the shelf, but at the same time, we also offer it in a limited version capabilities to the academia.
Okay.
For
So
example,
directly it will link with the production line.
No, it doesn't directly link with it. So you have to do a bit of configuration. What you have to do is, in this case, you have the work orders. Work orders are nothing but job orders. Job orders are coming, typically every plant will have an ERP system. Yes. ERP system is where you create your work orders. That work order has to be executed. That work order has to carry out certain steps and it goes through which machine has to be scheduled for this particular work order. So you get multiple work orders, right? Okay. You have to carry out multiple production orders. How you utilize your capacity and distribute your machines and capacities to different work orders is the scheduling activity. So it is not done automatically. There is a bit of somebody has to.
My point is, sir, Ravikirn sir, is it this package is coming with the ERP system or it is separate to that software? ERP
No,
system.
ERP system is about creating your transactions.
Exactly.
It is only scheduling software. So
Yeah.
what it does is, once you get the work order.
Okay, then after we have to interlink this.
Exactly.
Okay, sir. Thank you. Thank you, sir.
You're welcome. So I'll please don't mind if I'm running fast. I'll go to the virtual commissioning. This is a very interesting topic, and this is what I was talking about earlier. I'll certainly.
Any free softwares are there, sir, for student version or for learning purpose?
We do have not free softwares, but a very highly subsidized softwares for academia. Obviously, it comes with its own limitations in terms of the modeling capabilities. You cannot model a plant. You cannot model. You can only model an equipment and all of that. So we are already interacting. We work very closely with all the IITs. Even Aditya Institute has a part of our technology which they use in their course curriculum. So we'll be very happy if you are interested in any of these things. We have a team which is interacting with academia, and we have. Trust me here, I'm saying it because we take we put a lot of emphasis in creating the workforce of the future. So we invest our time and efforts, and even the software is heavily subsidized for institutions. So please do not hesitate to write to me. I'll share my email ID, and I'll connect you to with the right. There is a team dedicatedly working for academia in India, and they will connect with you, understand what you need, and then they will provide you with right solutions. Okay, virtual commissioning looks like I don't have a video, but as you can see here, this is the equipment, this right screen, and this is the control logic. Okay, so the idea is I first model it, but model is not just a dummy model, and it is not just kinematics. I'm building some kinematics, and so it's just moving. There is a logic controller that has this logic like on and off, amplification, all of that. The same logic input is sent into the virtual machine, and virtual machine behaves exactly similar to how a physical machine would behave. So what we do is we create a virtual model of your entire factory. We put this control logic, we bring these two together, the behavior and the body, and then run it as if the plant is running in real time, but not on the floor, but in your computer, and then see what has to be corrected. And only then, once everything is right, then you sign it off and then take it into the actual commissioning activity. That is what is virtual commissioning. Quality control and all of that okay, so I just pause here. This is what I have another 10 minutes. I'll cover shipbuilding quickly. Aerospace and shipbuilding industry have a very similar activities. So if I'm covering aerospace industry at that length, I don't have to spend so much time in shipbuilding. The only difference between shipbuilding and aerospace is a sheet metal, light metal, whereas shipbuilding is a very heavy metal, which is steel of thickness 10 mm and sometimes even thicker plates. Okay, so what we covered in digital manufacturing, you first model your plant, ensure that your plant can be modeled, right layouts, right flows, factory flow simulations, ensure that you have the right factory flows, right layout, only then you take it. But even before you do it, you also want to commission your line. So virtually commission your line by putting the behavior on top of the body, validate it, and then commission your plant. That's a factory and factory twin, how you are doing the factory. Once you have the right factory, then you have to ensure you have the right process of manufacturing. To do that, you carry out this NC machining and simulation, your robotic simulation, your part fabrication process planning, your assembly process planning. All of this is to validate your build and your fabrication activities in the virtual world before you put the process as a repeatable activity in the shop floor. So you are validating your plant and factory, you're validating your process. Only when you are certain of these two aspects, you're going in the shop floor. And when you do this, as I said, there is no undo in the real world. So better you do all those undos in the virtual world, get perfect at it, and then start producing. You will save a lot of time, a lot of rework, a lot of material, better quality, all of that. Okay, that's the idea of digital manufacturing in the aerospace and aerospace industry. As far as shipbuilding is concerned, a very similar concept. Okay, here, the most important aspect is how do you establish the digital continuity from your engineering world to the manufacturing world. So again, what to build? What to build is nothing but your work instructions or production documents. Shipbuilding industry is a little different from aerospace industry. It is a labor-intensive industry. That means the people on the shop floor are not that educated. They are contractual labor. They cannot understand the 3D models and hi-fi software. All they understand is 2D drawing sheets. So you have to transmit this information from a 3D model to a 2D drawing. So that's what they want to build and how to build. So these two things you carry out and you translate that into a easily comprehensible 2D drawings, which is what the workforce or the contractual labor on the shipbuilding industry understands and executes it. Again, similar steps. How do you prepare your data? How do you prepare your process plan? How do you prepare your plant layouts? Here also you can use a plant layout, scheduling. And shipbuilding industry is in a sense very not so organized in terms of layouts. If you go to a shipyard, you see plates here and there. The best industry as far as manufacturing is concerned is automotive. High-tech, specifically high-tech industry is the most automated industry. Then comes automotive, then comes aerospace. Shipbuilding falls way below in terms of these, the way they organize their manufacturing process. The reason is the ships are large, the parts are larger, the space is smaller. So you see when you go into a shipyard, the plates are always everywhere, and there are big cranes coming and putting these pieces together. It's a very labor-intensive activity. The idea here is just by creating dedicated spaces to put the material, whether it is a raw material arriving at the gate or it is a semi-fabricated panel or an assembly or a bracket or a deck or whatever that particular panel is, where do you place them so that you can easily assemble them and erect the ship together? So it is a different ball game. The nuances of it may vary a little bit from aerospace, but the principles remain the same. Okay, there also you can validate your process. It is a fabrication process. There also you can validate your, here also you can validate your assembly, which is also called erection. There are two steps here: assembly at a panel level and erection at a block level. So the complexity in shipbuilding increases a multifold as against aerospace industry. So, and then there it is riveting, here it is welding. So there is some additional capabilities in validating the weld quality and all of that. But otherwise the nuances remain the same. So I'll not spend much time into those aspects. So there are two ways to look at it. As you can see here, production engineering, and then create your structure. And shipbuilding is broken down into three or two key disciplines. One is your steel, which is also called as structure, because shipbuilding is predominantly a steel entity. Then your bought out items, your pipes and your accommodation, your HVAC, all of that. So that is called as outfitting. So there are two dedicated ways of producing these things. One is your structure preparation. This is where how you create a steel plate, how you cut it, what kind of holes you have to create, manholes and all of that, openings, and then stiffening. You have to put the stiffener so that there is no buckling of these plates, because you're talking about 10 by 10 long plates. Without stiffening, they tend to buckle, they tend to sag a little bit. So how do you do that and where to put that? Those are all, you can see this is what structure. Let me put a pointer here. The structure production preparation is where you talk about where are you stiffening, where do you put certain stiffener. So this creates a lot of drawings, and these drawings, through this technology, you can create drawings, and these drawings becomes handy information for the shop floor team, so that they know, okay, this particular plate I have to cut like this. There's the NC program I have to use, and these are the stiffeners I have to weld. The stiffeners have various types. There is a eye section, there is a bulb section. There are so many sections, and all those calculations are done at the design stage, the structural integrity calculations. So here we are not talking about design calculations. Once design is done, just giving that information on a paper or a 3D model, so that people can refer to what part or stiffener goes to which plate. Same thing extending to outfitting. Outfitting is about putting your pipes, putting your HVAC systems, putting your electrical harnesses. So how do you, because just to give you a statistic, One ship has almost 100 kilometers length of electric cables. One ship, the way it is, goes back and forth. That is the study. So 100 kilometers of wiring in one ship, and you have to be more. The space reservation becomes very critical. So 3D modeling is used to reserve spaces. Where will I run my electric cables? And they should not interfere with piping, because they should not interfere with my communication cables, because if there is any short circuit, my communication may go bad. If there is any leakage of the pipes, so there are so many rules that are built into this, so that you are ensuring that they are well designed. But again, this is all part of the design activity. Once the design is done, translating that into a manufacturing process creation methodology is what we carry out here. So very similar to what we have been doing, entire process planning, sequencing of operations, and how each operations can be validated in the virtual world. That's what we do here. I'll skip this video, and then once again, shipyard layout and simulation. We have seen that this particular layout, validation, and simulation has benefited shipyards more than aircraft shop floors, because as I said, aircraft shop floors are already well organized, so they may not get they may only get an incremental value. But in shipyards, the way they put this layout and all of it is so haphazard. With this 3D techniques, 3D validation and simulation techniques, they can first of all make the plant look more appealing, more attractive for the newcomers who are joining this job. And secondly, a lot of efficiencies can be built in. Once you have that layout, again, same production scheduling. I think somebody asked, once you have the ERP system, you get the order, then you distribute that order across various machines. You reserve berths, you reserve cranes, you reserve a gantry crane, because you have to carry out an erection activity. So there are so many ways of, in shipyard especially, there are so very critical equipment or critical resources. The dock is a critical resource. Once it's occupied, it cannot be given for other ship. Similarly, a gantry crane is a critical resource. So the planning and scheduling of these critical resources, so that they can be used in a shareable manner across multiple ship projects, is essence of this production scheduling and optimization. And manufacturing execution is another aspect which is not that relevant in shipyards, but at least till panel levels you can do it, because panel level is an automated line. After panels, it becomes more manual and manual. So we are trying to bring in this automation aspect even in shipbuilding, but up to panel levels. So if you're doing that automation, how you can automate it using IoT techniques and Industry 4.0 techniques is what is captured here. So again, similar principles like aerospace industry: validate your process, create work instructions and drawings for the shop floor people to consume, validate your shipyard layout and simulation, plan and schedule and optimize your resource utilization, and finally monitor your shop floor execution so that you are on track and on time. So that's the quick summary of yeah, that's where I have a lot of other slides, but I'll not jump into all of those. That brings just 10 minutes before the scheduled end of our session. I'll keep this 10 minutes for any question and answers. I'll be happy to take those questions. Otherwise, I'll hand it over to Srihari.
Yeah, any questions, participants?
Yes.
Please.
Yes, sir. My name is G.S. Reddy. I got some 3 small quick questions. Number one is, the single crystals are used for turbine blades. They're produced by GE some 40 years ago, I think, something like that. Even India also, the HL Koraput already pilot plant scale they did some 20, 30 years ago. So my question is that why these things are replacing the existing directional DS blades or the equiaxial blades, because they're going to extend the life of the engine, right? Why they're not replacing? What are the constraints?
I must admit that I may not be a subject matter expert on that particular topic here, because that particular topic requires expertise in those turbine blades or engine blades design and the materials that are used. But what I can do is I have a lot of. It's a very good question. If you can send a mail, I'll reach out to HL themselves and ask this question: why not this, and why are we phasing out those particular crystal-based turbine blade creation, and why are we going through these things? So my subject matter expertise is to bring digital technologies and enabling the physical activities.
Okay, thank you. I got the other question. Probably you can help. The 3D printing, additive manufacturing.
Sure.
In my opinion, it's for the very less critical products. Suppose if we talk about the what do you call single crystal air-cooled turbine blade, if we try to do by this additive manufacturing, you're just going to ruin the product actually, because you're going to additive manufacturing introduces too many defects.
That's right.
Which may be good for the less ordinary applications. Okay.
Absolutely, you are bang on point. Okay. There is an entity called CEMILAC in India. CEMILAC stands for it is kind of a certifying agency, right?
Right. I'm coming to that. Yeah.
You are aware of that. So CEMILAC clearly listed out what kind of components can be created using additive manufacturing, and those components have to be, first of all, within the aircraft. And there should not be load-bearing components. They should not be power generation components. So there are load-bearing components. For example, any landing gear housing or landing gear equipment cannot be with an additive manufacturing component. Any nacelle design, right? Because it has this the engines and propellers operating. The nacelle design, because it has so much of heat generation and all of that, cannot be with additive manufacturing components. So they have clearly demarcated what can be, and they're all very less critical internal. For example, your seat hinges can be additive manufacturing components. It's not that lead bearing component. So they have done that, and you're absolutely right. It cannot be used. That additive manufacturing technology has not yet reached a stage where you can use it for critical load-bearing components in aerospace.
Okay, sir. Got it. Thank you, sir. One last question. Does the digital manufacturing implements the airworthiness quality assurance testing and documentation is the question? Because here, lots of engineers will be hanging around when the manufacturing is taking place, type testing and all that they come, and too much of documentation, too much of harassment actually. Digital manufacturing is going to provide any good solution.
Absolutely, that's a very good question. There is something called virtual iron bird. Okay, so iron bird is a technique. You do it in these wind tunnel testing you carry out, right, for most of these aircraft components. Obviously, the physical testing cannot be replaced, at least in the aerospace industry. Automotive industry, most of the crash testing is now replaced with simulations. Today, there are certifying agencies that are certifying a car safety based on a virtual crash simulation using a software, because softwares have advanced to that level. And the safety, a crash on a road doesn't necessarily, there may be impact, the airbags can open up, and then, but a crash in the air, there is no other choice, right? It is disaster. So I think there are some virtual testing capabilities, but if you ask me, is it a replacement of physical testing? Not yet. So how they're using is virtual iron bird and virtual testing. When I say flight testing capabilities, they're only using it to arrive at the best alternatives. But the final alternatives have to be rigorously tested with physical flight testing activities. Unfortunately, no other choice.
Okay. Thank you very much, sir. Is it possible to have not all the complete PPT, but for general material for reading purpose from the point of view of the student and the
sure. I'll see there is some confidential and IP property. I'll do a bit of a dress down of this PPT. When I say dress down, moderate and remove some videos and materials and all of that. And I'll share this with the organizing team. No problem.
Thank you very much, sir. Thank you.
Ravi Kishanji, I am Professor Gupta.
Nice
I had been more than 24 years line manufacturing of aircraft division HAL.
Wow, okay.
Then I had been in materials procurement. I had been training and development deputy head of management academy. And past 22 years, I am full-time professor in management school.
So we should be listening to you, sir, than you listening to me.
I would love to from my area. But let me hats off your expertise and presentation, fantastic. I certify that best presentation I'm hearing today. No
Thank you
doubt.
very much.
And not only that, the flow, the keeping engagement, all this, it is one of the best I found. Now, only clarification I wanted to have, can I have an opportunity to see your factory, something which I am past 25 years before, and now 25 years later, what is in Dasu Aviation. In fact, we had a lot of what is called
Collaboration.
connection with Dasu while
That's right.
manufacturing components and then Airbus door and all.
Yes.
So if possible to have your contact and then your convenience.
Absolutely.
Because nowadays I am totally free. So I can have a kind of glance which you have seen in the presentation. That will update me further better, where I can transform or I can pass it to new generation, like the best job you are doing now.
Certainly, Professor Kishan. Thank you very much for your kind
I'm
words.
in Bangalore only.
Oh, very nice. So
Yeah.
nice of you. So once I come back to Bangalore, our office is in Jayanagar. Please
Okay.
drop in. I'll pass it on to Sri Hari, my contact details. Please drop in our office. We'll be very happy to host you, and probably we can rekindle your old memories of working with Dassault Aviation here.
And even from my area, I call it mind reprogramming. You can organize and make the people to hear me for an hour, half an hour, 1.5 hour session,
Yeah.
so that we can have some exchange of our
Absolutely.
learning and transformation.
Absolutely. That's a very nice thought of yours. I'll certainly do the needful, sir. Thank you.
So nice of you, but somehow connect me, because
Yes, we'll do that.
so nice of you. Thank you very much.
Thank you, sir.
Yes, one more question, query. Sirish Kumar, you have raised your hand. Please go ahead. Sirish Kumar. Yeah, I think, okay. Venkatesh, Ravi, is there anything else?
Yes, sir.
Oh, no, Shri, that's it from my side.
Okay, so Venkatesh, please summarize the session.
Okay, sir. So thank you, sir. As we come to the end of this enlightening session, on behalf of the organizers and the participants, I would like to express my sincere gratitude to Mr. Ravikiran sir for sharing his profound insights and experience with us today. Mr. Ravikiran begins with an insightful discussion on the evaluation of digital manufacturing and its transition to the virtual twins. The conversation underscored the pivotal role virtual twins plays in modern manufacturing by enabling optimization of the manufacturing plan before execution. This approach enhances efficiency and decision making across the entire product life cycle. One of the significant highlights was the introduction of V2R, virtual to the real approach, which bridges the gap between innovation in design and engineering and realities of the manufacturing. Virtual twins were emphasized as a key driver in advancing R&D, manufacturing, and value networks by enabling predictive insights and seamless integration. The evaluation of the product, plant, and process twins was particularly highlighted as a critical element in improving operational efficiency and fostering informed decision making. So, Mr. Ravi also delivers into the challenges and opportunities specific to the aerospace sector, including setting production rates, concerns around production quality and profitability and competitiveness pressures and the transformation of the supply chains to meet evolving demands. He emphasized the importance of innovation and digital transformation as essential enablers for achieving these ambitious goals while maintaining quality and efficiency. This session offers an in-depth perspective on the aircraft product life cycle, where he brought attention to the often overlooked significance of a manufacturing bill of materials. And also, he noted that many in academia and research focused primarily on the design BOM or EBOM, overlooking MBOM's critical role in bridging designs and practical manufacturing process. Additionally, he also discussed the particular aspects of shop floor operations, particularly product process research, navigation, and integration. His insights provided a comprehensive understanding of how these elements come together in the manufacturing environment to streamline operations and enhance productivity. I would also like to thank all the participants for their active engagements and enthusiasm throughout this session. Your questions and interactions have made this discussion even more enriching. We hope to continue such knowledge sharing sessions in the future and fostering collaboration between academia and industry to drive innovation and excellence. Once again, thank you, Mr. Ravikiran Garu, for your time and valuable insights. We truly appreciate your presence and contributions. So, with that, I officially conclude this session. Thank you all. Sriha sir, would you like to say anything?
Yeah, I can see there is one participant raising his hand. Any
Rajesh.
query? Yes, yes. Any query, Rajesh? Maybe you can quickly. Rajesh R.
So he has to unmute himself if he's speaking.
Yeah, he can do that. Yeah. Rajesh R, please unmute and raise your query if you have any. Okay. Probably that's something else. Okay. Though the session is summarized, maybe I am the right person to have a couple of words regarding my old friend Ravikiran, the Director of Manufacturing and Logistics at Dassault Systems India, for providing a transformative view of the radical changes industries like aerospace are experiencing in the current AI-driven area. Ravi's acknowledgement of AI as a tool for all engineering disciplines was especially inspiring for those of us in academia and research. His endorsement offers a renewed sense of optimism for the future of the engineering professions and our alignment with involving the industrial needs. The session was not only enlightening, but also a testament of the potential of virtual twins and digital transformation in reshaping the industries. Thank you, Ravi, for sparing your time. Though you are occupied with all your professional and business activities, you gave your time for me. Thanks a lot.
Thank you. Thank you, Shri. Thanks a lot, everyone. And please do not hesitate to write to me. I'll drop my email address to Shri Hari. And let's keep this conversation going. Learning is continuous. It never ends in a college or an educational institution. That's what I believe. So hats off to this continuous learning process, and have a great evening. Thank you very much.
Thank you.
Turning off. Bye.
All participants, you can give your feedback and leave the session, and let us meet tomorrow 6 p.m. Thank you.